Thanks for the introduction from the chairman. Before I start my presentation, I would like to thank the organizer to invite me to come to this beautiful city for a presentation. And also I would like to thank Professor Wang, but I'm not seeing him here.
Here, come back, okay?
Okay. All right. Okay. So I'm Wei-Hung from Taiwan Tech. Today my topic is related to a new technology using microplasma. And I know as a professor it's very tough to give a lecture or talk before lunch. So I will go straight to the main point, and I appreciate if you can bear with me to the last minute. Okay. So the main motivation we want to study this new type of plasma is that for conventional plasma, as you can see, this is a very conventional and very popular technology to do material synthesis and processing, but there are some drawbacks of the conventional plasma. One, you need vacuum system, means this is very costly processing. And since you need a vacuum condition to have a stable plasma, means that this is a batch process from the chemical engineering point of view. And secondary, since you need a vacuum, so it's very difficult to use plasma to have liquid chemistry processing. Due to these two major points, I'm thinking that if we can have the plasma running in ambient pressure stably, so that we can use this plasma to solve some problem. One, we can design a continuous process using plasma. Secondary, okay, Professor Wang come back. Okay, I would just like to thank you to invite me to come back.
Sorry about that.
And secondary is that if we can have plasma running in ambient pressure stably, we can use this plasma for liquid phase processing. So this can open a lot of ideas to do chemical processing and chemical synthesis. Okay, but the major point is that how we can have the plasma running in ambient pressure stably. This will need to explain in a lot of theoretical physics. Since we don't have time and our major is not physics. The main point is that if we can shrinking the size of the plasma from centimeters scale to micron scale, and due to this unique scale, we can largely increase the energy and electron density in plasma by a lot of order. Think about if we can shrinking the scale, length scale from centimeter to micron, we can decrease the volume by about maybe to 7 to 9 and 10 order by decreasing the scale. And in that case, we can increase the electron and energy density in plasma by increasing about 9 to 10 order. By such huge emplacement, we can make this plasma very stably running in plasma. So the major idea is that if we can shrinking the size from bulk size to micron size, we can have the plasma running in ambient pressure. That's the main idea. All right? Okay, as I mentioned, since we can have the plasma running in ambient pressure, so we can do a lot of interesting things. One is to design continuous process. But that's not my main topic today. I want to emphasize that since we can have the plasma running in ambient pressure, so we can do something more interestingly, which means that we can use the plasma to do liquid phase processing. So the first idea is that if we have the electrochemical cell like this, simply we can replace the cathode using microplasma. As you can see here, we use the platinum foil as the anode, and the microplasma can provide a lot of electrons from the plasma. And this can use as a cathode in a conventional electrochemical cell. By this, we can do a redox reaction. For example, if in the electrolyte, we have the metal ion, they can diffuse or convection into the interface of the plasma and liquid. At this moment, the metal ion will emit the high energy electron come from the plasma. At this moment, they can form the redox reaction. During the redox reaction, the metal ion can form metal atom state, and they can aggregate to form metal cluster and continue to grow nucleation. Finally, we can grow metal nanoparticle by this new technology. Let me emphasize the key advantage of using this type of technology. One, it's very fast. think about the conventional wet chemistry. You need hours to do the redox reaction. Depends on the chemistry in the electrolyte. But using this idea, because the high electron flux comes from the plasma, we can initiate the redox reaction in a very, very fast way. And you can control the current from the plasma, so we can control the reaction rate. And secondary, we don't need any reducing agent. Again, think about the conventional wet chemistry. You need sodium bromohydride or hydrogen, not such a very strong reducing agent to form the redox reaction. But here, we don't need any reducing agent. Why? Because the electron comes from directly, so we can form the redox reaction. So this is the green process. Finally, we can do some reactor design using microfluidic device or design some special microreactor. So potentially, this could be a continuous process. So I would like to show a video. As you can see here, we have the argon plasma, and the beam size is about 100 micron, and here is the platinum foil. And even in this demo, in the electrolyte, is the only gold tetrachloride solution in water, no other thing else. As you can see, after plasma treatment, you can see the color of the solution from clear turn to pink very quickly, within 10 seconds. I didn't change the time scale bar, so as you can see, this is a very fast reaction. So the major idea is that the high electron flux, okay, it's running, okay. So the major idea is due to the high electron flux come from the plasma, and they can initiate the redox reaction within the metal ion in the electrolyte. So you can imagine that you can use this technology to play with the chemistry as long as you can find suitable electrolyte in the solution. So not only the gold nanoparticle here, you can also play with silver nanoparticle and other metal oxide particle as long as you can find suitable electrolytes. Right? But another example, because silver or gold is too easy to do. So another example here is that I want to do something special. So one example here we want to do, as the Professor Lu just mentioned, we want to synthesize graphene quantum dot. The reason why we want to use graphene quantum dot is that graphene is a super material, but only high electroconductivity with no band gap. So one idea how to open the band gap of graphene is using the quantum confinement concept. What is this? As you can see, every bulk material has a band gap. If we can shrink in the size of bulk material to nanometer size, and due to this quantum confinement behavior, we can largely open the band gap of material. So this is a very typical example from the physical point of view. So if we apply this technology to graphene, graphene is a 2D dimensional material, so if we can shrink in the size of graphene down to about 10 nanometer, then at this moment we can open the band gap of graphene. And also the particle size, functional group, surface state, and edge effect can control the band gap of graphene quantum dot. So the typical idea is, that if we can use in microplasma, if we can find a suitable precursor dissolved in the electrolyte, maybe we can use this technology to synthesize graphene quantum dot. And by controlling the chemistry and plasma parameter, maybe we can control this factor in graphene quantum dot so that we can tune the emission of the graphene quantum dots. So in order to do that, we tried a lot of recipe, and fortunately I have a very hardworking student, so they tried a lot of recipe. And finally we found one recipe is working, which is using sodium dioxide sulfide, SDS. This is a very common surfactant you can find in your lab, also in your bleach. And this is the chemical structure of the SDS. This is a typical surfactant structure. And we use this surfactant, and the concentration is about 1% dissolved in DI water. And we use few drop of HCl to increase the solution conductivity so that we can have the plasma. And the interesting aspect of the SDS is that at this concentration is already above the critical micelle concentration of SDS. So in the electrolyte, SDS will form a micelle like this. So taking this could be a very nice carbon precursor, because this provides a template. This looks like a quantum dot or particle-like shape. So once we have the electron come from the plasma, an electron maybe will have some interaction or decombination, polymerization, and composition, all kinds of possible chemistry here, so that they can have the interaction between the carbon-carbon bonding, so that they can have some special process to form a chemical bonding. I mean special because I don't know the mechanism yet, we just have the data. So my student do the demo for me is that we use the H cell. So the anode is just a PT platinum foil, and the cathode is the plasma cell, as you can see here. It's time zero. So we use a Nafion membrane to separate two cells because we want to study which cell will initiate the reaction. As the time goes by, you can this cell, the solution getting darker, but this side is still clear, means that we don't have anything occur here, but this side we generate something. But if we want to prove that this graphene quantum dot, according to the theory, they should have the emission. So under the UV light, you can see this cell have the blue emission, means that we can generate something to have the blue emission. But convince you that it's the graphene quantum dot structure, we do the TEM study. As you can see, the particle here is very tiny. According to the histogram analysis, the every size about 4.9. And in order to know the bonding structure, we do a more detailed stamp. As you can see from the stamp and the diffraction pattern here, we can prove that the bonding is sp2 bonding. So in short, if we have the tiny particle with the sp2 carbon structure, all the evidence suggests that we have graphene quantum dots. The most interesting thing is the mechanism. So far, we are still thinking about the mechanism. We want to understand that. So in my mind, the story is that in the liquid phase, in the electrolyte, we have the SDS micelle here. And according to the literature, the micelle size is about 3.4 nanometer. And once they come to the interface of the gas and liquid here, and our plasma will provide high energy radical and electron. Once this high energy electron radical encounter with the micelle, maybe they have some polymerization. But what kind of polymerization we are trying to understand? Could be radical polymerization or other polymerization. But in short, this could be an idea how we can generate graphene quantum dot using the microplasma study. And as you can see here, if we can tune the structure of the micelle here, that could be one idea. We can tune the size of graphene quantum dot so that we can control the emission. Okay. To prove that the optical study, we do the POE mapping. This is a photoluminescence excitation, which means that this scale is emission and this excitation. So we change the excitation and collect the emission spectrum and generate a POE mapping here. So for the SDS as the electrolyte, we can see the mapping here. As you can see, the maximum emission is around 430, which is the blue emission. So as I mentioned in the previous story, if we can control the structure of the micelle, which we use the C-tech, which is another very common surfactant you can find in your lab, but the size is much larger. So if we use a larger C-tech as a micelle in the electrolyte and do the same plasma treatment, same problem at the same time, we will see that because the larger structure of the micelle here, we should have a larger graphene quantum dot. And according to the quantum confinement theory, if you have larger structure, the emission will be ratio because the band gap is smaller. So compare the two POE mapping here. If we think about the micelle could be a nice candidate for graphene quantum dot synthesis using microplasma. All right, so in addition to that, we want to do something more interesting because we can do more than one treatment using microplasma. So the idea here is that we do the synthesis to generate graphene quantum dot first. Then we put them into another reactor, have silver ion. Then we do plasma again. By this way, maybe we can synthesize hybrid. So the idea here, as you can see, if we do plasma synthesis 2 times, we pre-make graphene quantum dot here, then put them into another reactor and do plasma again. As you can see here, we are so surprising to see a jumbo structure like this. If we do stem EDS mapping, you can see here the bright is silver according to the mapping. and the darker one is carbon according to the STEM EOS mapping. So this proves that using microplasma twice or even more, you can do more complex material design and synthesis. And the most interesting property we found from this hybrid is that this is a PLE mapping for blue emission graphene content, as I showed you, using SDS as a template to synthesize. If we generate a hybrid structure here, you can see the photoluminescence has been quenched by the silver attached. This is very interesting phenomenon. The reason we think about because the overlapping of the UV absorbance of the silver and the PLE spectrum of the blue emission graphene content, as you can see. The blue line is the UV absorbance of silver, the absorbance about 400 nanometer, and the red line is the PL mapping of blue emission graphene content, so the emission is about 400. So they have a lot of overlapping, means that the emission energy from the graphene content could be the energy donor to be reabsorbed by the silver nanoparticle. So we see an energy transfer phenomenon between the graphene content and silver. Okay? So this seems like a very interesting phenomenon due to the band alignment between the graphene content and silver. So we can have the energy transfer between the donor and the acceptor. And this can create a lot of interesting idea because if we can tune the emission of graphene content, which means we can blue shifting and red shifting the photoluminescence energy of the donor. Also, we can synthesize different metal, for example, silver or gold, or silver gold alloy. If we can tune the emission here, then we can control the overlapping percentage of these two spectrums. Then we can control the energy efficiency between the donor and the acceptor. This can create a lot of interesting ideas for applications such as optoelectronics, capalysis, such as photochemistry, and biomedical biosensing. But I'm just a chemical engineer, so if you are interested about application study here, please come to me, we can discuss. And finally, as I mentioned, that if you pre-synthesize graphene content and do the plasma, again, we can have the jumbo structure. This means that we have the heterogeneous nucleation in this pair. But how about if we pre-synthesize gold using microplasma to synthesize gold nanoparticle? And do the microplasma again, can we have the gold and silver hybrid? Is that could be a kosher or different jumbo structure? Because the chemistry is totally different. So due to this idea, we pre-synthesize gold first, then do the microplasma again. We want to know the hybrid structure will be kosher or jumbo, or they are even just a separate phase. But the results show that we do a lot of very detailed STEM work. We found that this is one particle, as you can see from the EO mapping. This is a kosher structure, so inside is the gold, and outside shell is the silver. So which means that silver, gold, this chemistry pair in the microplasma chemistry, they are forming a homogeneous nucleation, so that we can have very homogeneous silver shell outside the gold core, which is totally different than previous example of graphene content of silver, which shows a jumbo heterogeneous nucleation behavior. But the major reason why we have such huge difference may be due to the atom, they have different lattice mismatching, or could be due to the plasma chemistry is totally different, but we are under investigation to know the whole mechanism. Okay, so finally, it's time for lunch, but as I mentioned, I would like to thank Professor Wang to invite me to here, because about 14 years ago, I was in his lecture in transport phenomena and membrane separation. And this morning, I have a very surprising feeling because 15 years ago, I was a student and he is a teacher. But 15 years later, we are here as an invite speaker, so we can give the talk again. So this is a very, very sweet moment, so we can meet again. So finally, I think this is a very exciting moment. We can meet here in Daejeon and share the research experience. And finally, take-home message is that microplasma is very interesting. So if you have any idea for cooperation from physics, chemistry, and engineering point of view, we can discuss it. Thank you very much.